Next up for this afternoon's discussion here at the NASA Office of the Chief Technologist Industry Forum, we'll be hearing about the Franklin Small Satellite Subsystems technology and the Edison Small Satellite Demonstration missions from Brant Sponberg, who's the program executive for those programs. Brant?
Thanks, Dave. The most important thing you need to know about me is not that I work for NASA, but that my wife is a Duke alumnus. If you follow college basketball, you know the Maryland Terrapins do not like the Duke Blue Devils. She warned me before I come here that I actually pose a security risk to all of you. So I don't know if that means the campus police are going to come drag me off, or if I'm just going to burst into flame, but just to be warned. Apparently this extends to spouses, not just alumnus. More seriously, I actually helped start the Centennial Challenges program in my first term at NASA headquarters. I'm now in my second term. I got to work with Bobby at the National Academies on a study on NIAC. So I'm actually very proud to be part of this new organization. And I'm here to talk to you specifically about two new programs, the Franklin and Edison small spacecraft programs. You are all familiar with this chart by now. The first program I'm going to talk about is the Franklin Small Satellite Subsystems Technology Program. It resides in our game-changing technology division. It takes proof of concept small spacecraft subsystems at the TRL 3-4 level and matures them through the mid-TRL gap to TRL 5-6, so that by the time they're done, they're ready for flight. These technologies may originate inside the early stage division in programs like SBIR, Space Technology Research Grants, the Center Innovation Fund, or they may originate outside the early stage division. They may come from other government agencies, from academic research, or from IR&D at corporations. The second program I'm going to talk about is the Edison Small Satellite Demonstration Missions Program. It resides in our Cross-Cutting Capability Demonstration Division. It flight validates small spacecraft technologies and mission capabilities in space, TRL 6 through 7, so that they can then be used in NASA, commercial, or other applications. And again, the technologies for this program, they can originate with Edison or within the game-changing division, or they can originate outside that division, elsewhere in NASA, in academia, or industry. We named these two programs after two of America's most prolific inventors, Benjamin Franklin and Thomas Edison, obviously. And we hope that these two small spacecraft programs are equally as prolific in terms of the inventions and innovations that they foster. I wanted to spend, before I jumped into the programmatics, I want to spend just a few slides talking about why we have two separate small spacecraft programs in the space technology program. One reason is that technological innovation is making the building blocks of spacecraft smaller, cheaper, and more powerful, and on a very quick pace. We see this in Moore's law, expressed here in the price of a transistor, which has come down 7 orders of magnitude over the past 40 years. We see it in the energy density of batteries, which have doubled in 10 years. We see it in the density of magnetic memory devices, so-called Kreider's law, which has improved 7 orders of magnitude over the past 50 years. We see it in the cost per hour of power in photovoltaics, which has improved by a factor of 5 over the past 25 years. We see it in the density of charged couple device arrays, which have improved in density by 6 orders of magnitude over the past 30 years. And we see it even just in the cost of doing a single computation, which is improved by a whopping 13 orders of magnitude over the last century. Multiple industries are spending billions of dollars of R&D here in the US and elsewhere in these and other areas. To leverage that spending, we need small spacecraft that can infuse these new technologies quickly and that can take advantage of these technologies to perform missions better and more affordably. Another reason why we're pursuing dedicated small spacecraft programs is to enable new approaches to traditional satellite uses, especially in communications and remote observation. If you look at the history of how most spacecraft have evolved, they start pretty large and they get larger, more capable, but also more expensive. We see this in the evolution of, say, the orbiting astronomical observatories to the Hubble Space Telescope. We also see it in successive generations of TDRS satellites. These are wonderful spacecraft with wonderful capabilities, but they're not fundamentally different approaches to spacecraft design from what's come before. But if we start small, depicted here in terms of 3U and 6U CubeSats, we can radically rethink how we approach spacecraft design. For example, we could imagine the evolution of a satellite made of 12, 24, or more CubeSat buses, where massive levels of redundancy reside at the level of identical, low-cost, mass-produced buses rather than specially engineered subsystems. Or we could imagine replacing monolithic apertures with multiple small spacecraft flying in close formation. Or we could imagine a heterogeneous constellation where perhaps you have a few long-lived utility spacecraft that provide utilities like power, communications, processing, maybe even optical paths for shorter-lived instrumented spacecraft that are traded out when new investigations are needed. These sorts of things won't make sense for every application, but they offer large advantages for many. The third reason why we have these dedicated programs is to take risks on new spacecraft applications. For example, in biological and physical research, the ability to get an experiment into the space environment, whether it's microgravity, radiation, or vacuum, whatever it is you're after in that environment, and take data rapidly and affordably is very desirable. Typically, these experiments take months, if not years, to get into space. The advantage of small satellites is perhaps we can get them there much more quickly and on a timetable that's more relevant to the research that's being done. A couple NASA missions, PharmaSat and GeneSat, have taken steps in this direction, but there's a lot more that we could do. For example, the ability to bring a small spacecraft or pieces of that spacecraft back to Earth would be greatly desirable in terms of bringing the samples back down and having the biological or material samples examined in laboratories back here on Earth. In-space servicing is another area where certain functions, not all, but some, may be better or more cost-effectively performed by small satellites, or perhaps even swarms of small satellites, rather than large spacecraft. Over the long term, these kinds of spacecraft may also play a role in remediating the growing orbital debris problem. A third potential new application is planetary research. Having small spacecraft complement our big planetary missions with penetrators, microrovers, and other capabilities. Over the long term, these kinds of spacecraft may also have a role to play in resource utilization, providing either small proof-of-concept labs or highly efficient factories for processing extraterrestrial resources. You'll note that all of these applications are different than the kinds of applications that were just on the previous page. These involve moving atoms, molecules, and larger objects around, not just photons. What's interesting is some of the technologies that underlie these capabilities, things like DNA sequencing, microfluidics. We're seeing the same kinds of trends, the same kind of order of magnitude decreases over years or decades in capability. These things are becoming rapidly more affordable, more powerful, and smaller. And again, this lends the technology well to small spacecraft. Now I'll jump into the programmatic, starting with the Franklin program. Again, the objectives of the Franklin program are to mature technologies that enable small satellites to provide game-changing capabilities for the government and commercial sectors. At completion, when you finish development of the Franklin program, the system should be ready for demonstration in space. So we're talking TRLs 3 through 4, up through about 5 through 6. We're anticipating an annual solicitation, a broad agency announcement, and I'll talk more about that in a couple pages. And based on the funding we have available, or we hope to have available, and the maximum awards we think we're going to be making, we'll have at least 2 to 8 awards each year. We expect those awards to have a 1-year base activity with up to 2 one-year options, and we're estimating awards that are in the $1 to $3 million per year range. And it's actually a topic I'm actually interested in having folks feedback at tomorrow's breakout session on. Are we sizing this about right, or do we need to think about smaller, larger kinds of awards? Collaboration, these competitions are open to everyone, academia, industry, and federal labs, and partnering is strongly encouraged. The Edison program, again, is to develop and operate a series of small satellite technology demonstration missions with game-changing and cross-cutting potential for government and commercial sectors. As secondary objectives, these missions may also provide science or educational value, and we're also hoping to improve secondary payload space access through this program, and I'll talk more about that later. So the TRLs we're talking about here are TRL 5 through 6 up through 6 through 7. Again, we're talking about an annual broad agency announcement. Based on the resources we have available and the maximum award we're looking at, we're going to select at least 1 to 2 missions per year, hopefully more. And these awards, we're anticipating that they would be 2-year awards to get ready for launch, not necessarily to launch, but to get the spacecraft ready for launch, and that there would be at least 2 gates, one for proceeding in development and one for the actual launch. And we're estimating that, that this 2-year would be funded at the $1 to $10 million range. Again, collaboration is wide open, academia, industry, federal labs with partnering. Let me talk a little bit about the management, not just the programmatics, but the management of these programs. We have one joint program office for both the Franklin and Edison programs. It resides at NASA's Ames Research Center. There'll be a firewall around this office to block it off from proposing NASA organizations or NASA organizations that may be proposing to these programs. Our Franklin program lead is Kim Hines at Ames Research Center. Kim, raise up your hand. She actually comes to us from the SBIR program, and so she has lots of experience with ground technology development. And our Edison program lead right next to her is Bruce Yost, and he has a long history of working small payloads and spacecraft missions way back, all the way back to the Space Shuttle Hitchhiker and gas can programs. Similarly, at headquarters, we have one PE for this program in the Office of the Chief Technologist. I'm currently that person. And again, we'll plan one annual solicitation that'll cover both programs. There won't be 2 separate solicitations. We hope that'll help us coordinate and make smart decisions between the 2 programs. And now I'll talk a little bit about that solicitation process. I think our solicitation process is fairly straightforward. It's going to start with a request for information. We've actually completed this first step. It closed June 30th. We had over 200 responses. That will help us provide inputs that will help us draft a broad agency announcement, which actually we're in the process of reviewing right now. We hope to release that broad agency announcement for comment, release it in draft form so that you folks can comment on it on or around August 9th. And then those 2 things together, the RFI inputs as well as the comments that we get on the BAA, we on the program side will look at them, but we also will have a technology assessment panel, which I'll talk more about in a future slide. They'll provide some external inputs to us that will help us draft our broad agency announcement. And right now, we're targeting that broad agency announcement release, that final release of that solicitation for August 1st. Folks will send in their proposals. We'll assess those proposals with the help of the technology assessment panel. Proposals will be scored. And then we'll develop a candidate portfolio of investments to be made. And then the program office at Ames will go back out, and those folks that are in the portfolio will have negotiations with you. Assuming those negotiations can be successfully concluded, we'll send recommendations up to Bobby, to the chief technologist to make the selection. Selection's made, awards are given, and we go into program execution. One thing I should mention, the RFI that I started off with there, some of you have probably seen that or responded to that. It represented our current list of a few people at NASA of what we thought would be a candidate list of small sat technologies. But again, we want your inputs on this. Again, this is a topic we could talk about tomorrow at the breakout session. Are there things we're missing on that list? Are there things we're not highlighting on that list? Or things that should be taken off that list? I threw a couple acronyms at you on that prior page, so I just wanted to say a few things about those. The first one is this Broad Agency Announcement, or BAA. It's the type of solicitation we're pursuing for this. And the reason we're going this route is because we do want this wide participation from teams made up of academia, industry, and federal labs. This gives us the greatest flexibility in terms of the types of awards we can make. We can make contracts, grants, or cooperative agreements. We can execute any of those underneath a BAA. And we'll select what we do depending on who the participant is, what our interest is in the technology or mission, and what your interest is in the technology or mission. Our BAA process is advised by a technology assessment panel, or TAP, which serves several functions. Its membership will be made up of approximately 10 non-proposers, people who can't serve on the TAP and also propose to this process, with experience from NASA, DoD, academia, and industry. There's obviously a lot of other small sat efforts at universities, at DARPA, at the Air Force Operational Responsive Office, elsewhere, NSF. We want those folks to serve on this tab, have a few folks like that serve on this tab so that we're aware of what else is out there and help us define what are the technologies, what are the mission priorities that we should be going after in this BAA. Also help us review the proposals when they come in and avoid duplication with other small spacecraft technology activities. Just one slide on our likely key evaluation criteria. They're listed up there, and I won't go through them in order. They're pretty typical. We'll start off with an initial reading based on the technical concept, followed by more in-depth evaluations of the technical merit and viability of the proposed concepts. But I did want to stress that this is a technology program. We're not interested in small sats for the sake of small sats. We're interested in small sats that go after game-changing or cross-cutting or ideally both kinds of technologies. In terms of game-changing, we're looking for technologies or missions that are major advances over the current state of the art or that support capabilities that simply don't exist today. And in terms of cross-cutting, we're looking for technologies and missions that benefit many potential customers and applications, not just a few. And so if you look at the box, you want to avoid the red and shoot for the yellow and the green. The other point I wanted to stress is that the final decision will be made considering cost and overall funding. While we don't want anyone to underbid the costs of their proposals, affordability will be an important function of the selection process when we put together that portfolio that goes up to Bobby. And so we do need proposals that are across a range of different costs. Space access for the Edison program is obviously important. I want to spend a few minutes on that. It's going to be a little bit different in some cases than the traditional method of matching a spacecraft to a dedicated launch on a specific date. For now, we anticipate that the Edison missions will launch as secondary or hosted payloads. And that kind of launch can come in two flavors. One is the participants, can propose a launch if you have access to a launch, propose it as part of your proposal, and if we select, you have your ride that way. The other way is government furnished, and we hope that in the BAA that we go out with, we will provide, likely as an appendix to the BAA, common government orbits, adapters, and interfaces on common government launches for you to design to. So that way you can design your mission, design your proposal to match one of those capabilities. You come in, if we select your mission and you get it developed, then we'll put you in the queue for a future launch. An example would be the International Space Station, the commercial resupply missions that will be starting in the next year or so. Those are missions that are going off at a very regular pace to a very specific orbit. That will likely be one of the things we'll include in this BAA as one of those government-furnished launches that we can provide to you if your concept can be designed to that and that's the appropriate orbit, the appropriate regime for it to be tested in. In the future, we would like to have dedicated small spacecraft launch capabilities. I was very excited by the Nano Satellite Launch Challenge announcement this morning. It's not coincidental, it wasn't an accident, that the goal for that is a single 1U CubeSat is the payload for that launch. I worked with Andy and a lot of other people worked with Andy to help define that prize competition. It's not just because we think it's going to do a lot of cool launch technologies, which it probably will, but also because we want to be a customer. My program wants to be a customer of those capabilities. And so if something comes out of that challenge, or if other independent industry developments occur, you should look to us in the future to have some sort of follow-on launch service procurement for those kinds of capabilities. Another thing that we're just beginning to look at is also interplanetary access. Ideally, we'd like to be able to send some of these spacecraft out beyond Earth orbit, whether that means we're reusing upper stages or they go on host spacecraft, perhaps geostationary satellites, whether the commercial or government may play a role here is TBD, but we want to let you know that we are looking at that. Although the focus is on technology, I wanted to touch on a few important topics that are of interest to federal commercial science education opportunities. Cost sharing is not a requirement for this program, and it won't be a selection criterion, but it is encouraged to the extent that proposals can come in with cost sharing. It allows us to make more awards and develop and demonstrate more technology. A big aim of this program is to coordinate with but not duplicate other federal small spacecraft programs. I mentioned these earlier. What we want to do is have proposals that build on funding from these other federal programs but don't duplicate the technology efforts that they're independently undertaking. As Bonnie mentioned, her program will work with commercial folks on flexibilities on commercially important issues, intellectual property, data rights, title rights and property. You could imagine someone setting up, say, an Edison mission that forms a certain breakthrough remote sensing capability, but after the primary demonstration phase is ended, they want to use that in a commercial role. We'll work with you to make that kind of capability happen. After selection, we anticipate that a number of these Edison missions will actually do scientific investigations in the course of their demonstrations. We also hope to offer, where it's appropriate, Edison missions up to the science community to become platforms for peer-reviewed missions of opportunity. And we'll work with NASA's Science Mission Director and Exploration Systems Mission Directorate to make that happen. In terms of educational opportunities, we anticipate that academia will play a big role in this program, and so we anticipate that there will be lots of hands-on university student involvement in many of these projects. We are also formulating a complementary university consortium or institute to complement the Edison and Franklin programs, and you'll hear more from us about that in the future. Just a few upcoming events to watch out for. We will be at the AIAA's, the annual Big Small Satellite Conference in Logan, Utah. On August 9th, we actually have a 2-hour town hall from 10 to noon Mountain Time there, where we hope to have a more involved discussion with the small spacecraft community. We're targeting the draft BAA release for on or about that time frame. Again, this will just be a draft release. We'll see comments from the community. And then we hope to release the final BAA on or around October 1st. My last slide, I just want to leave you with a few thoughts, specifically the thought that good things can come in small packages. And I wanted to provide one example. Although there's lots of examples out there, this is one that kind of caught my eye. I just wanted to highlight it as an example of the kind of thing we're looking for in this program. And the example is Pin Spacecraft. This is the idea that you can take a superconductor, put it on a spacecraft, on one spacecraft, and then have a rare earth magnet on another spacecraft. And the magnetic field lines from the rare earth magnet actually become locked in place because of the impurities in the superconductor on the other spacecraft. And that way you can have two spacecraft maintain relative positions without using propellant, without using mechanical interfaces. They'll maintain their relative interface just based on the magnetic field lines that are locked in place between those two magnets. And it's something that's very resistant to changes in the spacecraft. They really do lock in. This is something that's been an example that was, I think, first pursued at Cornell University by Mason Peck, and it's the sort of thing you could demonstrate with just a couple simple CubeSats. But if you demonstrate this kind of capability, it could lead to lots of bigger things in the future. For example, instead of building large apertures out of deployables, you could actually build them up out of small spacecraft. So you wouldn't have to worry about all the weight and all the mechanical issues associated with large deployable structures. You could actually just build up apertures out of very small spacecraft. Another example is you could do station keeping for large space structures. It's depicted here in the bottom as a space station without having heavy mechanical interfaces. You even think about things like fractionated solar sails and other kind of futuristic concepts which are captured by the middle image there. What's also interesting about this example is this is something that's actually been pursued through a couple programs that are now in Bobby's portfolio that kind of illustrate the system that Bobby's put in place here to bring technologies up through TRL levels and through different programs. Cornell actually, a bunch of Cornell students actually examined this technology on NASA's FAST program, which you heard from LK earlier today, to facilitate access to the space environment for technology that is now part of the Launch Opportunities program. And even before that, Dr. Peck actually investigated this under the old NIAC program. So you see both a technology that can lead to game-changing and has cross-cutting kinds of capabilities, but you can also see it moving up through those TRLs. But this particular one is one that it might be a ripe candidate for a small spacecraft demonstration. With that, that's the end of my presentation. We can take questions if there's still time.
I'm John Barr with ULA. I hope I didn't miss this, but for the Edison, you had a cost range of $1 million to $10 million?
Currently, yes,
Okay.
that's right.
Is that exclusive of the launch service?
It would, if you were proposing a launch.
Flying as a secondary.
Yeah, it's flying as a secondary. If you're proposing a launch, yes, and you have costs incurred through that you want to pass on to us, yes, that would have to be included in that cap. Something we can talk about more tomorrow at tomorrow's session if you're there. We want to get feedback on that sort of thing, but that's our current concept. Any other questions? Oh, one more.
Yeah, I have a question on the TAP. You mentioned one of the selection processes rely on the input from the technology assessment panel. So how do you actually select these panel members, organize the panel activities? And also another question is, when you are dealing with the selection of a competing server program, potential proposals, when you have tens of millions of dollars, and sometimes the two proposals are very different in terms of what they actually propose and implications to technology future. So do you have a set of predefined criteria and how to actually score them? Because you actually mentioned in your slides you actually score them. And how do you ensure the firewall actually works so the biases, possible biases won't be get affected in the selection of those programs? Because my thought is, because when I was working in Goddard, I was involved in one of the, we call the risk-informed decision process. Some of the major technology programs, you're making decision and you have a number of options, it's not so easy just to give a simple score. And sometimes involving use such thing like we call the analytical deliberative process. And so it has a formal methodology to apply to actually select the program that has the most potentials. Can you elaborate on some of those issues?
Let me address the bias question first. There's really three ways we get at bias. One is we do have this firewall. We expect the program managers to wear the big NASA hat to be with us here at headquarters, if you will, to function as a unit with us. The second way is that technology assessment panel. NASA will actually probably be a minority member of that panel. They'll probably have about a quarter of each of those four sectors that I had on that technology assessment panel. So you'll get that sort of broader DoD, academia, industry, they get that kind of broader look at what the state of the art is and where the technology priorities should be and how the proposals line up against those things. And the third way is our selecting official. It isn't the folks at Ames. It isn't me. It's actually Bobby Braun, our chief technologist, and he obviously wears a very big NASA hat. So I think through all those different ways, we should eliminate any sort of NASA field center bias in the process. In terms of the actual selection criteria, it's something we're working on now. What the actual scoring would be against those criteria. It's something we welcome thoughts. If you come to our session tomorrow, give us your thoughts. Is there something we're missing that should be in there? Is there? Do you have experience with a particular scoring method that maybe we should consider? We're open to all those sorts of things.
Thank you.
Thank you, everyone. Look forward to working with you.